Okay, so then I would once again try to do some experiment related to filters. I've tried it a couple of times already. It always somehow failed, so hopefully it will work today. But I would, to make this as easy to understand as possible, I would try to once again start with this simple example. So this is what we have looked at. This is also a first order low pass filter. We have some resistance, we have some capacitance. We have derived the transfer function using this cutoff frequency or corner frequency that depends on 1 over RC. And so this camera here is the rear camera of my laptop. I will maybe zoom out the camera a little bit. And so at first, as usual, I have some box here, and inside this box, I have a couple of components, and I have a breadboard, and this is the capacitor that I also used before in other experiments. It should be a 0.22 microfarad capacitor. And remember last time I successfully failed in measuring the capacitance of this using this nice multimeter here. And so maybe I need to go up a bit so that we can see the display. Because in this range, so there are 3 different ranges here to do the measurement. One range that goes to 2000 picofarad, which would be, I don't know why they write it in this way. It would be, like 2 nanofarads. And then there's one range that goes to 200 nano, so 10 orders of magnitude, 2 orders of magnitude, the factor of 100 higher. And one that goes up to 20 micro. And so even if nothing is connected there, it's measuring something. And what I've learned, and this is a nice learning, is you always need to compensate here. So there is this small knob, and with this small knob, you have to rotate until this shows 0. And the problem is, if you compensate this range won't be compensated, and this range won't be compensated. And so we need to have this range here because our proposed capacitor is larger than 200 nano. It's 220 nano. So we need to have this range compensated, and I think I need to turn in the opposite direction now. Turn it to 0. Okay. So then, unfortunately, this capacitor won't go in there. I cannot directly measure this capacitance. So I need some adapters, and so as adapters last time, I just had some paper clips. So I can have a paper clip here, I can have a paper clip there. And then connect this capacitor to the breadboard. Yeah, so that's connected. And now I have adapter cables that I can connect here and there. And so now it's compensated, it's measuring nothing. And we can connect one clamp here and one clamp over there. And so then it's measuring, and it's measuring 0.22 microfarads. So this nicely fits. Okay, so we have a 0.22 microfarad capacitor. And I can remove these cables once again, and maybe also remove the paper clips. And so then we need to have some resistor. And the resistor, I would use a 1 kilo ohm. So there's a box here of 1 kilo ohm resistors. I will take one out. And this time I also have measurement cables for the multimeter, and we can switch to the range to measure resistances, 2 kilo ohm range, and measure the resistance of this resistor, and then you can see it's fitting fairly nice to 1 kilo ohm. Okay, so connect the resistor once again to this breadboard. And now we want to measure the transfer function. And to measure the transfer function, we need another advanced instrument. We need to have some oscilloscope. So the oscilloscope is this one here. I think this is what I've shown before. And this is a PicoScope. It's USB powered. And it should hopefully connect to my computer and should be detected without problems. And there might be some bing bing somewhere because it's connected, maybe not. Okay, and we need probe cables. And the probe cables are here. And so there are 2 of them. And I will take one, which is now the yellow one for the input. And maybe I can make this a little larger for a second. So the input connects here, and the red cable is connected to the output. And both of these cables, I will check in a second, they have some switch here to switch between some attenuation of 1 and 10. And hopefully I will all both set them to 1. So let's check the other one here once again. Yeah, this is also set to 1. So this is to measure input and output voltage. And now we need to have a source. And for this, we will once again use this arbitrary waveform generator. And so there's a last cable that goes to this. And yeah, then I need to have a short breakout cable. This is the source here at the circuit, and this is where, oh no, this is the ground at the circuit. This is where the ground of my instrument should go. And so how do I get out of this full screen mode like this? Okay. So now we have set up the same circuit. And we can also plot this, and we could also directly measure it with this frequency response analyzer for this PicoScope. And now it's doing something and clicking. And so if we check from this values, R is 1 kilo ohm and C is 200 or 0.22 micro. If we calculate the corner frequency, omega C is 1 over R and C. We get this value, and if we from this calculate the corner frequency as the usual frequency divided by 2 and P, we get 700 something hertz. And so if, let's say, if we, right here, we have channel A for the input, channel B for the output, both attenuations set to 1. If we go from 10 kilohertz to 100 kilohertz with 50 steps per decade, then we should
the signal generator
and the signal generator, and the signal generator, that's a very good point, Cancel. The signal generator should of course be also meaningfully be connected to the input. I say, so always something fails. So this cable, of course, also needs to be attached there. So we will start once again, and we should start with 0 dB of gain with 0 dB phase or 0 degree phase. And this is 10 Hertz, this is 100 Hertz, around 100 Hertz. Okay, something might start to happen. And then here we should see a drastic drop of our amplitude response going down. And while this is measuring, I mean, I could do the same stuff here and say our frequency is again some log space between 10 Hertz and 100 kilohertz, and also have this transfer function here, which is 1 divided by 1 plus f divided by, or j times f divided by fc. This is what is written on my slide set. Okay, I should have escaped the output. And yeah, so here we can also do the same into figure 1, have a semi-log x plot. Of frequency and the magnitude of this transfer function, and 20 times log 10 of this should now give us the similar response. If I add a grid, similar response as what we see here, right? We start with 0, we have the same drop, we end with something below minus 40 dB. Okay, this makes sense. If I add a second figure, and inside the second figure have a semi-log x plot of the phase response of the angle of this transfer function, then after adding a grid, we should see the same as what we have here in the red curve. Mm-hmm. So this is looking nice comparison. Any other comments? No. Okay. So, okay, I think this is more or less what we did before. So then switching back to my camera and making this a little larger, I have another nice box. Or I can maybe rather use full camera here, some EMC demo kit, design your own filter from Würth Elektronik. And inside there are also lots of components, mainly common mode chokes, and also other capacitors. And some boards. The problem is that you need to somehow solder these components onto these boards, which is not so convenient to do it here right live now in a lecture. But there are some capacitors like this one here. And there's somewhere a table of these capacitors that, unfortunately, because the document camera is not really working, but this one should have 0.01 microfarad, so 10 nanofarad. So if we go back to this instrument here, and if I share my screen once again, so this is the multimeter. So now I should measure in this range here. Once again, I somehow need to compensate it to have 0 without something being connected, which is the case right now. And so this is this capacitor, and this capacitor hopefully directly nicely fits into this multimeter here. And so we can see, okay, we get not 10 nanofarad, but 9.6, something like this. Okay, so if now instead in my low pass filter here, if I instead of this capacitor take this smaller capacitor and also reconnect the ground to this, what would you expect if I repeat the measurement? In the frequency response analyzer that we have here,
the connect frequencies move for 90.
Yeah, so if this is getting smaller, then this should get larger. So the corner frequency, the break frequency should move to higher components. Okay, and so we can also try this out and say go. And then it's measuring once again, and it takes some time until this measurement finishes. And then we should hopefully see that this corner frequency goes to higher frequencies. I mean, I can try to do it here. Say C is now just 10 nanofarad, which is 10 to the power of minus 9. So yeah, I should, it would probably be better to also write this as a script. Yeah, so our omega C then gets a new value, the FC gets a new value, and the transfer function gets something new. And so the corner frequency in this case is then 15 kilohertz. So just in the kilohertz region, now this is getting down. And we could replot it in Octave, would get the same result there. Okay, so I mean, some other option to, what would be another option to build a low pass filter?
With an inductor.
Yeah, with some, we could also try to build a low pass filter with some inductor. So if we take some inductor here and a resistor like this, and if we would write down the transfer function, then it would be the same transfer function as here above, just that the corner frequency in this case is R divided by L. And so one L, one inductor that I have here in my box of components is this one. And this is a 1 millihenry inductor. And so, yeah, to be able to measure something meaningful, I think we cannot use a 1 kilohertz resistance in this case, right? If I take a 1 millihenry inductor and if I say omega C is R divided by L, then we get 1 megahertz of, or yeah, we would get FC is omega C. So we would get 150 kilohertz of corner frequency. This is way too high for our measurement here to be meaningful. So this corner frequency must be smaller. So how can we get this corner frequency smaller? With a smaller resistor. So let's take a smaller resistor, and I have lots of resistors here inside this, and there hopefully will be some, luckily I've all measured them and written some values on them. So here, for example, I have 10 ohm. So here's a 10 ohm thing. And so if I connect my instrument here once again, and if we go back to the range of measuring resistances, then this should be a 10 ohm resistor, 10.1, 10.0, not too bad. Okay, so let's get rid of on the breadboard. Let's get rid of the components that we have here. This was the 1 kilo ohm resistance, and maybe I can make this larger for a second. So there is the inductor connected as a series element, and here's my resistor, and for the resistor it somehow needs to, I need to bend the wires to be able to attach it to the breadboard. Okay, so this looks like this now. And so there is my input. This is the ground. And this is the output. And we can...
The signal.
And the signal generator. And I once again forgot about the signal generator. Okay, and so we can remeasure. And it's doing something, and in between, I will go back to my Octave thing. And so now we have just some resistance of 10 ohm used. So our corner frequency is this, and angular corner frequency is this, and corner frequency is this. So 1.6 kilohertz, something like this. There we should see some break, which is, here's 1 kilohertz. So somewhere here until there, we should get more or less 0 dB of gain, no phase shift, and then we should see the same behavior as before. So, interestingly, we don't start with 0 dB anymore, but with something less. Yeah, there was 0.6 dB. Why do we have this? Why don't we start with a factor of 1, a DC gain of 1? So overall, it does not look too bad. We could have maybe used a smaller resistor to move this corner frequency to smaller frequencies. Does not look as nice as for the RC filter, this LC filter, but still it's not looking too bad. So, yeah, why it's not working that nicely? Or why it's not, no, why don't we have 0 dB gain at the beginning? Because the inductor is made out of a wire, and the wire also has some resistance. So we have, even at 0 frequency, we have, if we check our schematic here, we have something like resistance divided by resistance. So there is some additional resistance here that somehow destroys our measurement result.